that would come out from a black body that, according to the classical theory, as is shown here in this picture, it should in fact curve uh, upwards, so that if you go to shorter and shorter wavelengths, higher and higher frequencies, there should be more and more energy contained in it. Because the oscillators can be excited to arbitrarily high frequencies. And this created a problem, because this means that one would have an ultraviolet divergence, as it was called, ultraviolet catastrophe. And he solved the problem by suggesting that you could only have energy quantized in little packets. And he introduced this object called Planck's constant, as it was later named after him. And this is also a dimensional quantity. And if we say that all energy is quantized in terms of Planck's constant of the action, as shown here in this equation, E equals h bar omega, then in fact, this ultraviolet catastrophe is averted. And this was really the beginning of quantum mechanics. One way to see the importance of quantum mechanics is to recognize that if we take Maxwell's theory of classical electrodynamics, then in fact, the electrons that are orbiting the nucleus should be losing energy all the time, because they're going round in circular orbits and therefore accelerating. And we know that accelerating charges radiate. So they should lose energy and they should collapse into the nucleus. And if you calculate how long this takes, it's of order a microsecond. So in fact, all matter should collapse within a microsecond. And obviously it has not done so. And the explanation for why it has not done so is that quantum mechanics prevents it from happening. And all these people who came to contribute to the subject, Planck, of course, I mentioned, Niels Bohr, Max Born, Erwin Schrödinger, Werner Heisenberg, and many others, they built on this theory and constructed the laws of mechanics that would actually explain or account for the behavior of, starting with hydrogen atoms, molecules, all of matter. This was a profound revolution. And for our purposes, it introduces the third fundamental constant in nature. Let me see if I can get rid of this line that is somehow crept up on this. I don't know. Okay, please ignore this yellow line. I don't know how that got there. So the next step in 1928 was that Paul Dirac combined special relativity and quantum mechanics. He constructed a theory that described how electrons, which are tiny particles, but can also move very fast, would be described by a relativistic equation. And this was one of the most insightful observations ever made in physics, to realize that that elegant-looking equation actually describes the behavior of subatomic particles. And it is this which ultimately led to the standard model that we have today of the unified electroweak interaction and quantum chromodynamics. But let me just point out that as far as, sorry, I think I have to get rid of this annotation. Yes. Okay. So in this picture now, we have not only electrons, but we have the quarks that make up nuclei and the gluons that bind them together. And we also, of course, have their counterparts in terms of the leptons, the electron and the heavier cousins of it, the mu and the tau. And they're partnered by neutrinos, which are neutral and have only weak interactions. Weak interactions are mediated by the gauge bosons W and Z. And the photon, of course, is the original boson. The gluon is also a boson. So as I said, Bose rules, okay. And these particles are not conserved in number. They can be infinite number of them. You can create and destroy them at will. However, the quarks and the leptons are fermions. Their number is conserved, which is why you can make solid objects out of them. And then there is the Higgs boson, which gives mass to all these particles. And we have a well-developed theory, a quantum field theory, which allows us to calculate the interactions of all these particles in a mathematically well-defined way. And that has therefore given us, for the first time, the possibility of explaining everything that we do in the laboratory in principle in terms of this fundamental theory. And as you all know, this enterprise culminated about now 12 years ago with the discovery of the Higgs boson, which had been predicted at the Large Hadron Collider at CERN. This was an amazing feat of technology as much as science, that we can actually today we can have the means to really test our quantum field theories at that level and directly excite particles which have not been around since the birth of the universe and see them decaying in these huge detectors, which are a marvel of creation, really. Thousands of people work on them, and they can rightly take pride in what they have been able to do. Now, the point that I want to make for the purpose of this talk is that although you have all these elegant formulation for the weak electromagnetic and strong interactions, a quantum field theory with a Lagrangian, as we call it, written up here. Gravity is still described now by the classical theory of Einstein. It is not a quantum theory. And so in the full action that we have, as we call it for physics, the Einstein contribution still enters classically. Okay, the other objects are all quantum; they involve Planck's constant, but not Einstein's theory. So we still do not have a quantum theory of gravity, and let me explain to you why that is necessary. So, in fact, some question can be raised: do we actually need to quantize gravity when we have a perfectly good classical theory of it? And the point is that indeed, if we look at the mass of the Higgs particle and ask, so all in quantum field theory, all these quantities that we measure, they depend on what energy we measure it at what scale we measure it. And there is a framework called the renormalization group equation, which actually tells us how to connect measurements at one energy to measurements at another. So, for example, you're familiar with the fine structure constant, 1 over 137. That is its value at low energies, at the energies that we are living at. If you measure the fine structure constant at the Large Hadron Collider, it will actually be smaller because it changes as you go to higher energies. And similarly, the Higgs mass, which is measured to be in this range today, it's actually more like 125 GeV. If you run it up to high energies, it is perfectly consistent according to the renormalization group equation, with giving a description of physics all the way up to the Planck scale, which I'm about to introduce. So really, there is no obvious need to quantize gravity. But Einstein, in fact, in a letter, gave the same motivation for quantizing gravity as we encountered earlier for why one should quantize the other forces. Just as electrons going around a nucleus in an atom would be expected to emit electromagnetic waves and thereby lose energy, in fact, we now know today, because we have observed this in nature, two masses that are orbiting around each other also radiate gravitational waves, and these were famously detected by the LIGO detectors just a few years ago, as we know. So the electron going around the nucleus should also radiate gravitational waves. And therefore, Einstein's argument was, in that case, ultimately the electron would collapse into the nucleus due to the radiation that it loses. And therefore, you needed to quantize the gravitational theory in the same way that you had to quantize the electromagnetic theory. Now, actually, to tell you the truth, the time scale for this process is very, very, very long. So it is not really a pressing problem. I leave it to those who are interested to work out as a homework problem how long would it take for the electron to collapse into the nucleus by gravitational radiation. But this is a good point for me to backtrack a little bit and go back to something called the Bronstein cube of theories, which was constructed by this physicist, Matvei Petrovich Bronstein, who was a student of Landau. Unfortunately, he did not live very long. He was sent to the Gulag by Stalin and died quite young. But he realized that you could, in fact, try to construct all of theoretical physics with the three-dimensional constants that had been introduced by previous physicists. So we have, if you recall, Newton's constant of gravity, we have the speed of light, and your Planck's constant of action. So Bronstein constructed this three axis here. We are at the center, which is classical mechanics, where h bar is unimportant, where the velocities are small compared to the speed of light, and where gravity is unimportant insofar as space-time is locally flat. But if there is a limiting speed in nature, and I plot 1 over c along this axis, so that we actually don't live at the origin of this coordinate system, we live here, then we have to adopt the theory of special relativity, which tells us how to deal with dynamics of particles that are moving at speeds which are substantial compared to the speed of light. But if the speed of light were infinity, if there was instantaneous action at a distance, then you would be back to the origin. Similarly, if h bar were 0, if the quantum of action was 0, so then our propagation would be effectively according to the classical trajectories that we already know from classical mechanics. But because h bar is non-zero, in fact, there are multiple possible trajectories, and the bundle of those has a width of order h bar, and this is famously Heisenberg's uncertainty principle. But if you are a subatomic particle and the action over your trajectory is comparable to h bar, then it is not possible to simultaneously determine both your position and momentum, as you know. And that is when you have quantum mechanics. And in fact, if you then try to unify special relativity and quantum mechanics, you have quantum field theory, which is this point here. And similarly, if you go up to, you switch on Newtonian gravity, you have the theory up here. And if you combine Newtonian gravity with special relativity, you have the general theory of relativity. So Bronstein did all this, and he recognized that therefore, what we are really after is this theory of everything, which is this apex of this cube, where you have all three constants playing a role. The constant of special relativity, the speed of light, the constant of quantum mechanics, Planck's constant, and the constant of gravity, G Newton. In fact, there is one more apex here, non-relativistic quantum gravity, which is also interesting, but I'll focus now on this theory of everything, as it has been called. What are its scales? Well, from those three constants, we can construct a length scale, and that length scale is tiny. It is 10 to the minus 33 centimeters. It's such a tiny time scale that we can only discuss it in the context of the early universe. In laboratories today, we have only gone down to a scale of about 10 to the minus 16, 17 meters at laboratories like the Large Hadron Collider. The time that light takes to cross a tiny distance like that is called the Planck time, and that is also a tiny time. It's 10 to the minus 44 seconds. I mean, we are familiar with microseconds, which is 1/1,000,000th of a second, or a nanosecond, which is 1/1,000,000th of a second. And some of you might also know about attoseconds and so on, which, even smaller. But this is very, 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 very small. And the corresponding scale of energy or mass is very large. We like to talk in terms of energy because this is what we deal with in particle physics. So this is 10 to the 19 GeV, to be compared with the energy scale of 10 to the 4 GeV, which we have achieved at CERN. And in terms of mass, it's not that large. It's about 10 to the minus 5 grams, but we are talking now about fundamental particles. They don't carry that kind of energy. So, in order to construct a theory that combines all these possibilities, quantum field theory and general relativity, there are many approaches, and I'll sketch out for you very briefly the many people, name the many people that have worked on it. So, one approach is called the canonical approach. So, I cannot describe it mathematically in this lecture, but I'm going to give you a kind of a very impressionistic overview of the landscape so that you can see how what the basic ideas of it are. The other approach has this. So this approach, canonical approach, was largely followed by people who are coming from the general relativity side, and the covariant approach is largely followed by people who are coming from the quantum field theory side, right? And so that dictates the direction they take towards that vertex of Bronstein's cube, starting with the theories that we know about, as is indicated in these arrows here. Now, both loop quantum gravity and string theory have been successful at describing black holes and, for example, measuring the amount of information they contain, at least for extremal black holes. But so far, they have not been able to address questions such as the initial singularity of the Big Bang or the cosmological constant problem of vacuum energy. There has been a lot of development as outlined in this review by Carlo Rovelli, from which I've taken this picture, starting from the 1920s over the past century. And all the key words of the various things that have been discussed are mentioned here. So some of you who might be studying quantum field theory or general relativity would recognize these keywords that are listed here. But I want to get to the modern day. So passing through the 1970s, which he calls the Middle Ages, to the Renaissance, which began in the 1980s, about 40 years ago, we had the development of both loop quantum gravity and superstring theory, culminating in the current era. And there we have a fully developed string theory, as it is called. And people have also been looking at loop quantum gravity, where the background is not taken to be Minkowski spacetime as it is done in string theory, but in fact, it is considered to be dynamic, being generated by the candidate theory itself. To be fair, even in string theory, the propagation of the strings themselves should create self-consistently the space-time in which they propagate, but that's a much harder mathematical problem. What I want to do in the remaining part of my talk is to focus on this label here that says quantum gravity phenomenology. Because the point is that all this mathematics is very beautiful and elegant and very, very difficult, I should also say. But as Steve Carlip, one of the key practitioners in the field, mourned, the nearly complete lack of observational and experimental evidence that could point us in the right direction or provide tests for our models is the most daunting problem of quantum gravity. Because as we all recognize, ultimately we have to test theories by asking whether they agree with nature. So where are those tests? How can we do this test? I showed you that the energy scale of quantum gravity is 10 to the 19 GeV, and that is about 10 to the 14 orders of magnitude above the energies that we are now exploring at the Large Hadron Collider. So the Large Hadron Collider, we are up to something of the order of 10 TeV, so that's 10,000 GeV, 10 to the 4, and here we are talking about 10 to the 19. Now, there are various ways in which people have been thinking about how to test quantum gravity phenomenology. It is really difficult for the basic reason that there are very few predictions. Neither of these two approaches to quantum gravity have made explicit predictions for observables that can be measured and tested to see if they agree with the theory. But there are various ways of testing the fundamental quantities that enter any theory of quantum gravity, such as the fundamental symmetries of the theory. And what I'll focus on is tests of some of those symmetries, such as Lorentz invariance in particular, which is the key thing that underlies ultimately special theory of relativity and is preserved in quantum field theory and in many versions of quantum gravity as well, in particular string theory. So if I see any departure from Lorentz invariance, which I might expect to do at high energies, then that would be indirectly a test of quantum gravity, even in the absence of any actual postulates today as to how or to what extent it might be violated. And if quantum gravity actually leads to some strange behavior of space-time at the Planck scale, such as the space-time foam that I showed you in my top slide, which was this idea of John Wheeler, that space-time is a maelstrom of black holes appearing and disappearing on the Planck time scale constantly. And so, there is no notion of a smooth metric anymore, and space-time is a very, very dynamic environment. Then maybe we can probe that by studying the behavior of particles which are quantum mechanical and are propagating through space-time, such as neutrinos, which undergo oscillations. And I'll discuss briefly whether one could see decoherence effects on neutrino oscillations by space-time foam. So all this sounds like science fiction. And what is interesting is that today I can actually talk about potentially making this test using experiments, not in the laboratory, but which are been constructed to study the universe out there, astroparticle experiments. So first of all, just to say in very broad terms, without any particular theoretical motivation or justification, that we have kind of a general expectation that all these symmetries that we hold sacred, like Lorentz invariance or CPT, CPT is charge, parity, time, the idea being that if we invert all these three, then the physics should remain invariant as quantum field theory does. But these may not be respected by quantum gravity effects at the Planck scale. It's kind of a generic expectation. Okay, it's not a theoretical prediction as such. In particular, it doesn't happen in string theory, in the current formulation of string theory, because there Lorentz invariance is preserved by fiat, by construction. So if we actually detect it, then it would immediately falsify the current formulation of string theory. So that is good enough motivation. Now, there are technically, we try to parameterize our ignorance about new physics by writing down so-called effective field theories, and their terms that might violate Lorentz invariance or CPT or other fundamental symmetries would appear as so-called non-renormalizable operators. I will not discuss that today because those are technical, very technical topics. Just to let you know that there has been a lot of work done along these directions for those who are interested, and these are some of the reference to papers that have discussed these matters. I'll talk about how I kind of got into this about, what is it now, 1998, so quite some years ago, over 25 years ago, we observed that if there is violation of Lorentz invariance at the Planck scale, then we can in fact try and detect this by observing pulsed or intermittent pulses of photons from distant sources in the universe. So the point is this, that there are objects called gamma ray bursts in which a object like our sun, a whole mass of the sun, is converted into gamma rays in a very short period of the order of few minutes or hundreds of seconds. And that burst is therefore so powerful, so intense that we can see it right across the universe. But when we receive this pulse, it has structure in it, time structure, which is of the order of tens of milliseconds. So all we noted was that this pulse has traveled across the universe. So it has taken of the order of billions of years to travel to us, and yet the millisecond structure has been preserved. And so if you realize that that pulse is actually the sum of many different frequencies or energies, and in order to preserve the coherence of that structure, all those frequencies have to be traveling at the same speed. Otherwise, they will go out of phase with each other, and that pulse structure will be smeared out. So he pointed out that if there was any kind of a energy-dependent dispersion of light, anomalous dispersion of light in vacuum, which was proportional to the energy, and in the denominator, you would have the quantum gravity scale, which you might take to be 10 to the 19 GeV for the reason I gave you. then we could actually try to detect this on the sky. So this paper was published in Nature, and I just saw yesterday that it has now had over 1,300 citations. So it did really have quite an impact on the field, because people had not realized that you can, in fact, try to do this kind of tests using data that is already available from objects or satellites or telescopes that are been constructed for other reasons. So in fact, the satellite that is being referred to in this slide is called GLAST, so Gamma Ray Large Area Telescope, which in fact was renamed the Fermi telescope after it flew. It's basically a large silicon detector, such as similar to the ones that are there in the experiments at the Large Hadron Collider, about a meter cube, and it has been a very, very successful mission. So what they did was to observe gamma ray bursts. So for our purposes, let me just say that a gamma ray burst is, as I said, some mysterious phenomenon out there where a lot of energy is certainly released and undergoes very, very complicated, plasma dynamics. There are blobs of plasma shot out at very high Lorentz factors who create shocks. There is radiation in the form of synchrotron and also inverse Compton, we believe, from the collisions of these plasma balls with the ambient photons. And out of this comes that gamma ray burst. Now, needless to say, these are theoretical ideas. They have not been completely substantiated by data. But in any case, we are not really worried about the actual mechanism. We just want to notice that these pulses have a millisecond time structure even after propagating for 10 billion years. And that's what gives us the sensitivity that I pointed out. And the glass people took this seriously, and they said, well, we do actually have a lot of these gamma ray bursts, thousands on the sky, and the energy they release is very, very large. And we know their spectrum and we know their pulse structure, and we can, in fact, therefore, detect many of these as they have done. They have actually a gamma ray burst monitor on glass. And using this, they did a simulation of how well they would be able to tell any anomalous dispersion in the arrival time of the light signals according to the ansatz we had given. Now, this formula here, in which the velocity of the photons depends on the energy, is a pure speculative idea that it could actually be less than that of the speed of light by an amount which depends on the energy divided by the Planck scale. So if gamma ray bursts are at GeV energies, this term is 1 part in 10 to the 19. It's a tiny, tiny correction. But these people showed that it is actually detectable. It would give rise to this characteristic curvature in the photon energy versus the arrival time, as is shown in the simulation. And they said, yeah, we can do this. And they did do this. And the first object that they did this with, this was 10 years later in 2008, actually showed an interesting indication that if you plot the pulse structure as a function of the energy, then, as you see indicated by these red lines that I've drawn here, this pulse seems to be being delayed increasingly in proportion to the energy. So this is KeV energies and this is GeV energies. And there is in fact some indication of a linear trend with the energy. And they, in fact, interpreted this conservatively as setting a bound on the quantum gravity scale. And actually, as you see here, it is pretty close to the actual Planck scale. So in other words, they had the sensitivity to look for this effect. And this paper created quite a furore. But then another object that they looked at, which was much closer at a redshift of 0.9, the previous one had been at a redshift of 4.3, much, much higher. Here, all the photons arrived at more or less the same time. So there was no time delay here. Okay. And therefore, they were able to tighten their bound a little more by a factor of 10. But that's really because this most energetic photon, which you see here, by one of them actually arrived at the same time as the low energy photon. That could have been by chance. After all, we don't know the actual mechanism of gamma ray bursts, if there is any intrinsic dispersion in the source. So we are, really being opportunistic, trying to see if nature might give us by sheer luck, a hint for something really exciting like the violation of Lorentz invariance. Now, another set of objects where you can look for this kind of phenomena are called active galactic nuclei, which are supermassive black holes that are at the centers of all galaxies, including ours. But in many galaxies, unlike in ours, that central black hole is feeding. It is swallowing up matter and shooting out jets of plasma. And again, the details of the mechanism by which radiation is emitted are under discussion. But we see TeV gamma rays, much higher energy. And occasionally there are flares in these gamma rays that are coming out of these active galactic nuclei. Uh, and that again then gives us a laboratory to test Lorentz invariance. And this huge telescope on the Canary Islands called MAGIC actually in 2007 did a press release saying that they had in fact seen a 4-minute time difference between the arrival of a high and a low energy photon from a galaxy which is about 500 million light years away. And, obviously you would have expected both these photons to have arrived at the same time. But in fact, according to what they observed, there is a steady trend of the pulse to the right, as you see here, between 150 GeV and more than 1.2 TeV. And this gap is now of the order of minutes because these are much higher energy photons. So the time lag, according to that formula I showed you, is higher, even though the distance is a lot smaller. And so therefore, they had comparable sensitivity to Lorentz invariance violation at the Planck scale. Now, to cut a long story, I mean, this story has been continuing. People have been doing this. And here is a plot from John Ellis and Nick Mavromatos from 2011, which collected all the data around that time. And you see, most of them give null results, but some of them seem to indicate a time lag delta T over E gamma, which was increasing with the distance to the object, as you would expect, according to our simple model. And this is very intriguing, but the error bars are, as you see, quite large, and we could just be fooling ourselves. And this, in order to establish something as important as Lorentz invariance, you need a lot better data than this. But that data is now coming. There is the Cherenkov telescope array, which is being constructed, which would have a lot more and bigger telescopes to study the arrival time of photons from large distances. Let me turn to a different arena. The highest energy particles in nature, and we are looking at high energies because that is where you expect this phenomenon to occur. Now, they are actually cosmic rays. And to study cosmic rays, you have to go to remote regions like this is in Argentina, where we have a detector called the Pierre Auger Observatory that occupies 3,000 square kilometers. So here I'm with a colleague sitting on top of a tank, and the tank actually has detectors in it to detect the air showers created by cosmic rays when they enter the atmosphere. And this one that I'm sitting on is one of these little dots in this picture here, which covers a large area. There are 1,600 such detectors. And then there are telescopes surrounding it on the little hills around. Those are the Andes Mountains. They can see the light from the air shower on a moonless night. And we see when the shower comes in and hits the air shower array, we can see the activity on the ground and also in the sky through the fluorescence radiation. And here is an event that actually, it's amazing when you're on shift and an event comes in with an energy of 10 to the 10 GeV. So as I said, there's 1,000,000 times higher than the energy of the protons that is circulating in the Large Hadron Collider. And we have no idea how nature creates these very high energy particles, but we are studying them because in order to even create such particles, you have to have massive accelerators. If you wanted to do it with LHC technology, that ring would have to be the size of the orbit of Mercury. But nature somehow manages to create these perhaps in active galactic nuclei, in the extended jets of radio galaxies, maybe in gamma ray bursts. And we don't really know the answers to this. There's a very active field of research in cosmic rays. But for the moment, we are interested in simply asking, is there any evidence of Lorentz invariance violation in the interaction of these cosmic rays with other ambient particles? For example, as they propagate to us through the universe, they see the photons of the cosmic microwave background. And at sufficiently high energy, although these photons are very low energy, they are only 3 degrees Kelvin, so their typical energy is a milli-electron volt. But to a proton, which is traveling at with a energy of 10 to the 11 GeV, they look like a 100 MeV photon through the Lorentz boost. And that creates a resonance called the delta plus, and that causes the protons to lose energy. And that should cause a cutoff in the spectrum. And as you see here, there is a cutoff in the spectrum at the expected point. It's called the Greisen-Zatsepin-Kuzmin cutoff. Now, we are still debating if what we are seeing is really the cutoff or whether it is the source is switching off. We don't really know. But nevertheless, what is clear is that we are not seeing any violation of Lorentz invariance, because if so, then the flux would have continued beyond this point, and we don't see that. So it turns out, after some initial false alarms, that we don't have any evidence of Lorentz invariance violation in high-energy cosmic rays. That brings me to my last topic for today, which is that apart from cosmic rays, which are protons and heavy nuclei, the smattering of electrons and even antimatter, we also have cosmic neutrinos. And neutrinos, as you probably know, behave quantum mechanically. They oscillate into different types, different flavors. They oscillate between each other. And therefore, they provide us an excellent laboratory for studying quantum mechanical phenomena. And if we can detect them from cosmic messengers, then we also have very long baselines over which we can study their propagation. So it was realized quite some years ago that we could use neutrinos to study violation of Lorentz invariance, equivalence principle, another fundamental tenet in physics. We could really test whether there is indeed space-time foam at the Planck scale by observing neutrinos which are propagating through that and which would be affected, their oscillations would be affected if such a thing exists. Now, to study neutrinos, we need to high energy neutrinos, which is advantageous from this point of view because they give us a significant improvement over low energy neutrinos such as we see from the sun. We improve in our sensitivity to the kind of phenomenon we are talking about because we can look over much larger path lengths than the distance between us and the sun. And the energies can be up to 100 TeV as opposed to 10 MeV or so for the sun. So we have a very powerful probe here in potentially of whether fundamental symmetries are broken in nature at high energies. So just to illustrate the point, if I generate neutrinos through pion decay, pions decay to muons, which decay to muon neutrinos and electrons. So ultimately, what we would produce would be electron neutrinos and muon neutrinos in the ratio 1 to 2, and we don't make any tau neutrinos in this process at all. But because they oscillate between each other after they propagate long enough, this ratio becomes democratic. They become equally distributed. So this is what we should see if we look at a very distant source. We should see roughly equal numbers of electron, mu, and tau neutrinos. And any process that can affect the oscillations can change this ratio, and that is something that we can actually detect. Okay, so here I was going to discuss very briefly how the usual 1/3, which is the probability for finding a neutrino in the original flavor it started out with, would be affected if the neutrino oscillations coupled to a bath, such as quantum gravity might provide at the Planck scale. But I will not discuss that here. Let me just talk about the experiment with which I'm also involved at the South Pole called IceCube. And as it shows here, IceCube is actually buried under the ice between 1.5 to 2.5 kilometers deep. And it is obviously a very hostile environment. You know you're at the South Pole because, as you see here, all the directions point to north. And even in the high summer, the temperature is down to minus 95 degrees. Now, each of these strings that goes down 2.5 kilometers and is instrumented for about 1 kilometer is a cable like this. And on the cables, there are hanging this kind of digital optical modules, which are photomultipliers in a pressure casing, which has to withstand several hundred atmospheres of pressure. And these detect light, which is emitted in the ice as neutrinos create muons and electrons and taus by hitting ice body. And we actually see the light from the products of the neutrino interaction. Neutrinos themselves are, of course, invisible. Here is a quick video to show you how this experiment actually works. We drill a hole in the ice, first a little hole in the top fern, as it is called, in order to make room for a hot water drill, which generates, many megawatts of power, and which then drills down to, as I said, 2.5 kilometers. And that hole then takes about a couple of days to freeze up again. And meanwhile, the technicians lower those strings down that hole. And those strings are carrying these digital optical modules that I mentioned. And so when all this is done, we have a kilometer cube instrumented under the ice and are ready to detect neutrinos, because when the neutrino comes in and interacts and generates, say, in this case, a muon, the muon would be traveling faster than the speed of light in the ice, where light travels slower than it does in vacuum because the light has a refractive index. And this is Cherenkov radiation. It's like a bit like a sound boom for a plane flying supersonically. So here it's a light boom, and it's sort of bluish, pale blue light, and we can detect it with our photomultipliers. And by measuring them and using a lot of very clever technology, including machine learning, we can reconstruct the tracks, and we can even do astronomy. But the basic process that is happening here is called deep inelastic scattering, in which a W boson is exchanged between the neutrino and the nucleus that it hits, and it creates an outgoing charged particle. Actually, you have had one event where the neutrino, in fact, an initial electron antineutrino, hit an electron in the ice and created a W boson, which then decayed. That's the Glashow event, but that needs something like 7,000 TeV energy. So, as you may know, IceCube was able to detect cosmic high-energy neutrinos. These were our first two events at huge energies. In fact, they were initially named after characters from Sesame Street. This is Bert and this is Ernie, but we soon ran out of names because we have now got lots of these events. And this detector is able to determine the flavor of the neutrino. So a muon neutrino creates a track like this, whereas the electron or a tau neutrino creates a blob like this, because the outgoing lepton, the electron of the tau, has a much shorter range than the muon, which is the minimum ionizing particle. Now, the tau neutrinos can also create the so-called double bang events, but this is a simulation. This is not a real event. However, we have just seen the first tau neutrino events. A paper will appear in Physical Review Letters within a few weeks. It has just been put on the archive 2 days ago. So we are in a position very soon to measure the flavor ratio of the cosmic neutrinos that we are seeing from distant sources. And this triangle plot shows you on each side the fraction of tau neutrinos, muon neutrinos, and electron neutrinos. And in the picture, as the red dot, is what we should be seeing if, in fact, the neutrinos started out in pion decay, which is the most typical scenario. We should see roughly equal numbers of all three flavors. If instead they started out in neutron decay, in which case you had only anti-electron neutrino produced and no mu or tau, then we should see a ultimate flavor ratio, which is this green triangle. Our current data is in fact shown by this big red line here, right? This loop. But as we build a bigger detector, this uncertainty will decrease, and we hope to actually get to this little yellow ellipse here in due course. Now, what this plot also shows is that anything that is within the standard model of particle physics must lie within this region that is marked here in black. If we see an answer which is actually in this blue region here, dark blue region, that could be new physics. For example, neutrino decay. That's a possibility that we can test experimentally. But If you have Lorentz invariance violation, then we can actually be sensitive. The answer can lie anywhere in this triangle, depending on the actual theory of quantum gravity that predicts the Lorentz invariance violation. And we'll therefore be, as you can see here, by making a measurement that is as good as this yellow ellipse here, we'll be sensitive to a very wide variety of possible violations of Lorentz invariance, which can give us different flavor ratios through making this measurement. So this is a very powerful probe. However, to do this, to reduce that uncertainty in that measurement, as you see here, we have to, this yellow thing relies on something called Gen 2 or Generation 2, which is the projected uh, upgrade, or rather next generation of Ice Cube. The Ice Cube upgrade is in fact instrumenting the inner part with higher resolution. But we want to construct a much bigger version of Ice Cube, which will be, 8 to 9 times as big as the present one, which is already quite big, and instrument it a bit more sparsely, so it won't actually cost very much more, and also add possibly detectors on the surface which can detect neutrino, and which therefore will enable us to have a much larger active volume. And the time scale for this is not very distant. It will be within the next 5 to 10 years. And so we hope that with this detector, we'll actually, in fact, get the data that will enable us to measure that flavor ratio in the way that I described, would be able to constrain any departures from the usual expectation for neutrino oscillations over very long baselines. And one effect that could decoher neutrino oscillations over astronomical baselines is quantum gravity, because although it is happening on a tiny, tiny scale, the Planck length, there are many, 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 many Planck lengths between us and the distant source of neutrinos. Now, I'm happy to report that India is in fact a member of this IceCube Gen 2 collaboration led by the Tata Institute in Mumbai. Mohammad Ramiz is leading the effort. And so we will actually be making a contribution, hopefully, to this very ambitious experiment, which will not only do neutrino astronomy and neutrino physics, but also perhaps tell us something which is of fundamental importance to theories of quantum gravity. So let me end there because I'm sure there'll be some questions by making my key points, which is that we do not really have a full-fledged theory for quantum gravity. We have approaches towards it, of which string theory is the most well-developed today, but there are other approaches like loop quantum gravity. And there is a general expectation that the ground state of this theory can violate fundamental symmetries of nature. And if these effects are, in a effective field theory language, if they're of order energy square over the Planck scale, then we'll observe anomalous dispersion of high energy photons. There are hints for this in the current data, but nothing definitive. However, more data is soon coming. Much more likely, because of the dimension of Newton's constant is inverse mass square, we would expect the effects to be of order E cubed by Planck mass square. So if you are observing, say, TeV energy neutrinos, then we are talking about 10 to the 19, 10 to the 3 cubes, so 10 to the 9 divided by 10 to the 19 square, 10 to the 38. So you're talking about an effect of order 10 to the minus 29. You're talking about detecting something of 1 part in 10 to the 29. But even such a tiny signal can actually be probed in principle by studying neutrino oscillations. And so the experimentalists are ready to make these measurements. In fact, they're doing so anyway for other purposes. So what we really need now is explicit predictions from theory for what we can actually measure in order to be able to pin down the theory of quantum gravity, because without such predictions, it is kind of hard to assess, sample the entire possible parameter space. We really need some theoretical direction. Now, I'll end by quoting Wolfgang Pauli, who, as you all know, was a very, very famous and very smart physicist. He, in fact, came up with the notion of the neutrino. And in his later life, he also thought about quantum gravity. And he said, that is a very important problem, but it'll take someone really smart. In other words, even Pauli could not crack it. Okay, and I then think, therefore, that this is not, we physicists are kind of, in a strange sense, we are actually quite modest, in spite of having the standard model, which is surely one of the triumphs of, a mathematical description of reality. We are unsatisfied. If we want to go beyond the standard model, we want to discover new phenomena that prove everything that we have done so far wrong. And the fact that we have failed to so far solve quantum gravity at that level, we don't see as a failure. We see it as a challenge to the next generation. And I think that is a good point for me to stop. Thank you.
Thank you, sir. It was really informative. It's new to me, and I think all the students here joined, whoever joined here, and all the young faculties, young researchers here, actually enriched with this information. So now I would like to request Dr. Tamal Kumar Mukherjee, Associate Professor of Department of Physics, for question answer session.
Uh, uh, Sir, should I read it for you? Some of the questions from the chat
I
box.
can see the chat box, so let me read
Yeah.
out the question and again. So Anjana Case asks, did string theory encounter any limitation or drawback as of now? Well, I should say at the outset that I don't work in string theory, but I can certainly answer this question, which is that string theory is a mathematically extremely complex theory. So the ultimate goal of string theory is to be able to have a self-consistent description in which the space-time that strings propagate in is generated by the motion of the strings themselves. That is extremely ambitious. So far, the constructions that have been made that I'm aware of take the background space-time to be Minkowski space-time, the same as the space-time of special relativity or quantum field theory. Now, that, of course, still leaves an extremely complex theory, and I'll address some of that in the next question I see in the chat box. But what I'm trying to say is that you might consider it a limitation that it is in fact formulated on a space-time that has Lorentz invariance built into it. But of course, you could argue that that is the only way that in which you can proceed for the moment. So I would not call it a limitation or a drawback. I would simply say that currently that is the level that our mathematical technology, if you like, today can deal with. And I'm sure that in the coming years, progress will be made further in that direction. Now, the second question is from Aishwarya Roy, who asks, what is the physical significance of the 10 dimensions of space-time as predicted by string theory? Why did the extra dimensions deem such importance? Well, again, this question really should be answered by a string theorist, but my answer would be that we learned, this was in 1983-84. I remember Green and Schwartz provided the proof mathematically that in 10 dimensions, if string theory is formulated in 10 dimensions, then it is anomaly free. Anomalies are objects that show you that your theory is sick. There are states of negative probability. And what these two authors showed is that when formulated in 10 dimensions, there are no anomalies in the formulation of string theory, which is a good thing. In other words, string theory lives very happily in 10 dimensions. The only issue is that we don't live in 10 dimensions. We live in obviously 4 dimensions. So then the point is, where are those 6 dimensions? And as I showed you in the top slide of my talk, the expectation is that those strings, extra dimensions, are curled up very, very small on the order of the Planck scale or maybe slightly bigger. So that what we think of as a point in space-time is actually 6 dimensions curled up on very, very small scales. So we can't directly see them. and we can't ever probe them if they are only possible to open up at high energies. So it's a bit like, if you look at a little ring from a long distance, it looks like a dot, but if you get close by, it looks like a ring. Okay. And it could be even more complicated object, but the structure is not obvious unless you get very close up to it. And that in our language here means observing it at very high energies. And we don't have the energies to directly probe the extra dimensions of space-time, but they are crucial for its mathematical consistency. Okay, let me go on to the next question, which is if elementary particles get mass due to the Higgs boson, how the massive Higgs boson gets its own mass? Well, that is the beauty of the Higgs mechanism. The Higgs boson, in fact, of course, as the name says, it's a boson, but it's a scalar particle. It has no spin. It can couple to every particle that is there in the vacuum, and that coupling is what provides the mass to those particles, but it also has a self-coupling. So normally when particles in quantum field theory have mass, they violate the underlying symmetries of the theory. And so it looked for some time that a quantum field theory of the fundamental interactions, weak, electromagnetic, and strong, that it could not be constructed except for massless particles. And the beautiful realization of all the people that I've named earlier, including Higgs, was that it is actually possible to spontaneously violate the underlying symmetries without explicitly violating them. In other words, the ground state of the theory violates the symmetries, but not the underlying Lagrangian. This is the notion of spontaneously broken or spontaneous or hidden symmetries. It's an amazing concept, and one that more people ought to appreciate. Is one of the truly profound things you have learned about nature. And so the Higgs mechanism was actually, if you like, a mathematical loophole by which you could give particles mass without violating the underlying so-called gauge symmetries. And it was not until the Higgs boson was actually discovered at CERN that we realized that nature had actually chosen the route that Peter Higgs had noted was a possibility. I'm not sure if I make myself clear. There was really no guarantee that nature had chosen that route, but nature chose to follow that route. I mean, isn't that amazing? That we, mere mortals can write down a mathematical equation, and it turns out that the entire universe has chosen to obey that equation. I mean, this is like absolutely miraculous. Okay. Amarpal Singh says, that's not a question, sorry. Then Devendra Singh says, is Higgs boson give mass or Higgs field? Well, the Higgs boson is a field, like every particle is a field. The electron is a field, quarks have fields, the Higgs boson also is a field. It's a coupling to that field by other particles that gives them mass. Then Aishwarya Rai asks, would quantizing gravity solely suffice to unveil the unknown of the singularity inside a black hole? Well, the black hole is an excellent laboratory for discussing quantum gravity, and as you probably know from your question, there has been a huge amount of progress already made in understanding black holes, the thermodynamics, from an information theoretic viewpoint, and aspects of black holes which are semi-classical, in other words, quantum effects, but in a classical background space-time. There is an expectation that quantum gravity will indeed resolve some of the contentious issues about black holes, but that I cannot discuss in detail here. Okay, I think I've come to the end of the questions.
Can I ask a question, Papia?
Yes, ma'am, please.
Yes.
Thank you, Professor Shakar, for wonderful talk, particularly this experimental things which giving the foothold of the theoretical ideas, different theoretical ideas. I just want to know a very simple thing. The neutrino oscillation is basically for determining the mass of the neutrinos, right?
Well, the scale of the oscillations is determined by the mass square difference of the neutrino states, and also they're mixing with each other. They quantum mechanically the objects that describe them, the wave functions, mix with each other. Yes.
I just want to know if these cosmic neutrino ratios, which are going to experimentally determine, will
Yes.
give us some limit on the mass of the neutrino, which is a very, I mean, crucial things to know about the
Right.
mass.
I understand your question. Well, so the neutrino oscillations that we already know and have studied in great detail. So there are three types of neutrinos, right? Electron, mu, and tau. And so there are two mass differences. And when we study the oscillations of neutrinos that are created in the atmosphere by cosmic ray collisions, they are propagating over length scales of order hundreds of miles to thousands of miles when they're coming from the other side of the Earth. And those oscillations have been studied in great detail by experiments, initially by Kamiokande and Super Kamiokande, which are underground detectors, and the Sudbury Neutrino Observatory in Canada. And today we are studying them in IceCube, for example. These oscillations are well understood. The mass square difference in that case is of order about 10 to the minus 2 electron volt square. Very, very tiny mass difference, right? But an even smaller mass difference is implicated in the oscillations of solar neutrinos, which are traveling to us for the Earth-Sun distance, which is much longer. It's something like 8 light minutes, astronomical unit, something like, 93 million kilometers, right? But they are much lower energy. They're MeV energy neutrinos. And there the mass difference is even smaller. In both cases, the mixings are quite large. But when we take neutrinos, so we already know about the mass square difference and the mixing angles of neutrinos pretty well from these experiments that I mentioned. So what we do is, if I say that now some distant source like an active galactic nucleus or a gamma ray burst is emitting neutrinos, when they propagate towards us, what will happen is they'll start oscillating, but then the oscillations will get faster and faster because the objects will start mixing with each other more and more. So ultimately, they don't oscillate anymore. You get the beam will contain 1/3 electron neutrinos, 1/3 muon neutrinos, 1/3 tau neutrinos, and that's what will arrive at Earth, right? The oscillations will be washed out. I should have actually shown a plot indicating that. So what we can now try to detect is the so-called flavor ratio at Earth. We are not actually directly determining the oscillations. To do that, we have to do an experiment on the length scale of the oscillation scale. And the oscillation scale for these mass differences is, as I said, of the order of, at most millions of kilometers. But we are looking for much, much larger distances than that, right? And as for the limit on the mass of the neutrinos, that doesn't really come so much from oscillation signals, but in fact, we do get a limit on the mass of the neutrino from cosmology. And that's in fact something that my ex-supervisor at the Tata Institute, Nath, first proposed back in the 1970s, I think, long time ago. He pointed out that if neutrinos had a mass of even tens of electron volts, that they would actually dominate the mass budget of the universe. The relic neutrinos from the Big Bang would dominate the dark matter. And with much more work subsequently, today we believe that neutrinos can't be more massive than of order an electron volt from cosmology, because if they were the dominant part of the dark matter, then they would wash out structure on small scales, and that's not what we see up in the sky. So, in fact, a lot of our knowledge about neutrinos today comes from cosmology as much as it comes from laboratory experiments, and the two are complementary. You need both to study different aspects of neutrinos.
So this IceCube experiment can predict something about the violation of Lorentz invariance, which you were discussing?
No, it can't predict anything. It's not it's an experiment. The predictions will have to come from theories. But what it can do is to directly see if the flavor ratio of neutrinos we are seeing at Earth is what is expected if Lorentz invariance holds. If you see any departure from that, then that would indicate that Lorentz invariance may be violated, right? But of course, if you see a departure from what we expect, that could be due to other reasons as well, not just Lorentz invariance violation. So then the task will then become a matter of pinning down what the reason is, right? And that would require inputs of other experiments. That is why I keep emphasizing that it will be good to have some explicit predictions for what we can measure, which will allow us to test these fundamental theories. But the problem with the theory of quantum gravity is that it is such a difficult task, such a challenging task, that it is, so far, there have been very, very few actual predictions. If I ask somebody who has been working on quantum gravity from the theoretical side, can you tell me how a null geodesic would propagate in your quantum gravity vacuum? A null geodesic being a photon, or how a neutrino oscillation should behave. It would be difficult to answer that question presently. So we need to make more progress on that.
Thank you.
So may I have two short questions?
Yes.
So you may have said that, but I didn't follow. So what is the rationale behind the assertion that the quantum gravitational ground state may violate Lorentz invariance? That is the first one. And if we say that the Lorentz invariance is there to start with, and the ground state lost this invariance, then is it kind of spontaneous symmetry breaking of thing? These two questions.
Okay. So about the first, the key word there is may. As I have emphasized several times, we have no hard theoretical prediction. The expectation arises simply from observing that Lorentz invariance is a property of space-time of special relativity. So in other words, we construct a metric for space-time in which signals can at most travel at the speed of light, photons, and they carry all the information. Now, if you ask yourself, is this the metric description of space-time likely to hold up to arbitrarily high energy? The thought arises that as you go up to energies comparable to the Planck scale, space-time itself might become a dynamic object, and there have been lots of speculations along those lines. In other words, there might be enough energy density in a given small volume, enough to make it collapse into a black hole. And that black hole would be extremely short-lived. It would then evaporate again, right? So space-time might become a very dynamic maelstrom of, forming and evaporating black holes. This is a possibility that was dubbed space-time foam by John Wheeler, who was a famous physicist who talked on, as you know, gravity. So these are all speculations. They have not been given rigorous mathematical formulations, right? But there are general expectations that the ideas that we formulated based on our notion of the framework, the fundamental framework being space-time or the metric, whether these concepts will survive at high energies is an open question, right?
So if we
so therefore it's just an expectation. It is not a. That's why I've deliberately said may. But this violation, to answer your second question, how is Lorentz invariance actually violated? It could be explicitly, it could be spontaneously. And when I say Lorentz invariance, there are, of course, two parts to it, to this group. There is isotropy, and then there is boost invariance.
Exactly. Yeah.
So you might say, you might have a background field in the vacuum that picks out a certain direction that would violate the isotropy of the Lorentz invariance. And that is something easy to test for. Does the universe have a direction, as far as fundamental processes are concerned? So if we, for example, find a signature of a preferred direction in studying neutrinos at IceCube, that would be a probe of that kind of violation of isotropy. But that is actually already proved very, very precisely by all kinds of clock comparison tests in the laboratory. And so far, there is no indication of that. Okay. Another possibility is that you preserve isotropy, but you violate boost invariance. And that is something that has been mathematically formulated. It's called it's so-called kappa Poincare algebra, deformed Poincare algebra. And kappa is a dimensionful quantity. It's basically the inverse of the Planck scale that enters there, or the quantum gravity scale. And in that framework, you can ask for the, what the dynamics of particles would be and what the departures from special relativity would be. And one example was called doubly special relativity, but that turns out not to be consistent for macroscopic bodies. But there is a very active area of research in which people are engaged there. It makes a connection to non-commutative space-time. So normally, the space-time that we deal with, the variables commute with each other, but you could imagine capturing effects due to quantum gravity in form of a non-commutative space-time. The problem then is that when if I want to actually test these ideas with experiment, I would need to be told what to look for. Okay,
Exactly.
what anomalous dispersion might I see? And that calculating that is non-trivial in these suggested ideas, but work is continuing.
Yeah.
So that is what I'm urging theorists to do.
Thank you. Thank you very much.
Thank you very much.
Papia,
Okay, so I think it's very difficult to end this discussion on this topic, but time is limited, so we have to stop now. But I think there are more questions, so I would like to request all of the participants to write to me. I will convey to sir. I think Dr. Sarkar would love to answer those questions through mail.
Well, whatever
Okay,
I
so
can
at this.
answer, I'll answer.
Okay, sir. So, okay, so at this moment, I would like to request our HOD, Dr. Momita De, madam. So please come forward for a vote of thanks.
Yes, Papia, thank you. I was listening to this lecture thoroughly. So it was a wonderful lecture. And esteemed guest, our speaker, Professor Shubhi Sarkar, distinguished faculty members, and dear participants, on behalf of this Department of Physics, Admas University, Kolkata, I extend my heartfelt gratitude to Professor Sarkar for sharing his invaluable insights on this intriguing topic of quantum gravity. His expertise, I'm sure, have enlightened us all, enriched us, and have further inspired us, particularly the young students, to explore this fascinating field. I would also like to thank each one of you for your, all the participants, especially for your active participation and engagement, especially what just witnessed from this question answer session in today's seminar. So let us continue the spirit of curiosity as we dig deeper into this mystery of universe. And thank you once again. And we look forward to future for such enriching discussions further. Thank you very much. Have a wonderful evening, all of you.
Thank you all.
Thank you.
Thank you, sir.
Thank you so much for
Thank you.
coming.
Thank you.
And we like to see you in our campus once in next.
Absolutely.
Yes,
I'll be sure
we
to
all
visit.
would love to see you.
Thank
Yes,
you.
sir.
The next time, please
Yeah.
tell us when you are coming, then
Okay.
we can organize the talks physically.
I'll do that.
Thank you.
so
Thank you
much.
so much, sir.
Bye for
Thank you so much. Bye
Bye.
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 Bye, sir. Okay, so already the
Can be stopped now.
feedback
The live
link,
recording.
yes,
Please ask.
feedback link is already there. You can fill it for generation of certificate, and I think I can share it again. So, needless to say, we can only tribute to such exceptional scientists like Satyendra Bose, with uninterrupted skillful learning and serving science, serving society. So this is the moment to take a note. With this positive thought, I am concluding the session here. Have a nice day ahead, and thank you so much for your participations. Thank you so much, our team. Hope to see you soon, maybe in our next event. Thank you so much.
Thank you. Thank you.
Last but not least, I would like to thank the IT team, especially Mr. Ranabruto Chanda, and we are grateful to Mr. Abhishek Boshak and Mr. Shaunak Choudhury for the nice digital flyer and all technical support. Thank you. Thank you all.
Thank you. Okay, bye.
Thank you so much.
Thank you. Thanks again for such a wonderful webinar.
Thank you, sir.
Thank you. Thank you, sir, for your feedback. Thank you, sir.